right before the exam, and then in the lab we talked about buffers. I said, okay, in this next lecture we'll go over buffers a little bit more. And there was some extra things that we could have talked about in the acid-base lectures, but we'll leave those for now. It was just things like how do you, if you have a salt that's a mixture of a weak base and a highly positive charged cation, you can get a solution that's either acidic or basic. But that's fine, that you probably won't see that in the future anyway. So there is some extra stuff and extra practice in those lectures if you feel like you need to work on ice tables a little bit. This thing with buffers is probably the last thing you're going to be doing with ice tables. So I know, like we're finally over ice tables. I'm sure you guys are tired of seeing ice tables. So today will probably be the last time you look at them. Well, and also for the next quiz. So buffers will be on the next quiz. But then the next exam will be pretty much all thermodynamics and electrochemistry, right? So then they'll be done. And we'll kind of move on to thermodynamics, which we might find it a little bit more interesting than equilibrium the same way. We'll be looking at it from a different perspective, movement of energy, rather than just movement of concentration and physical movement of ions. All right, so buffers, we talked about them in lab last time. And so buffers are solutions that have a little bit of something that resists a change in pH when either base or acid is added to it, right? So in this left example here, you have pure water. And when you add a little bit of hydrochloric acid to the solution, you get a change in pH right away, right? Because hydrochloric acid is what kind of acid? It's a strong acid, right? And strong acid means what? It 100% it dissociates in solution, right? So that means that as soon as it goes into water, you get H3O plus or H plus CO minus, right? And that, as soon as we change the concentration of H3O plus in solution, we get a change in pH right away. With a buffer solution, you usually have some specific pH range that the buffer works at. You add some acid to it, and you get a very small change in pH for the solution, right? So here we see after you add the hydrochloric acid, you go from a pH of 9.43 in the buffer solution to 9.3. And so there are two mechanisms or two types of buffer solutions. Really, they're the exact same type of buffer solution, just depends on what the more common version of the weak acid or its conjugate base or weak base and conjugate acid you use. And so it's either a solution of weak acid and its conjugate base or a solution of its weak base and conjugate acid. Right? So if we have acetic acid, which is what we have right here, acetic acid, what would its conjugate base be? You get it'd be C2H3O minus, right? You lose the proton, and that's the conjugate base, right? Because if we have our, just to review, our acid reaction, when it reacts with water, H2O, it donates its proton, so water acts as a base in this case, and we get H3O plus in solution, plus the conjugate base, which is C2H3O2. Sorry, I forgot the 2 here. Minus, right? So that was our acid. So this, I shouldn't do it in terms of acetic acid, I'll just do it in terms of a generic conjugate base, right? And so you guys made a buffer solution, and so you didn't add just the acetate ion. How did you add acetate? Does anyone remember how you added acetate to solution? Usually you're not going to have just a fully negatively charged liquid. Right, you got a negative charge there. You do have ionic liquids, but they're a little bit more complicated. This is acetate. Does anyone remember what we added? What do you think you could add to this to neutralize the charge? Or what would you need to add to a -1 charge to get it to be neutral? A positive charge, right? And so a common way to do that, to make a strong electrolyte, would be to add something like sodium, right? And so if you add sodium acetate to solution, that's generally how you're going to add the conjugate base in this case. right? So you made a solution of acetic acid and sodium acetate, right? They're both weak acids, and acetic acid is a weak acid, and acetate is a weak base, right? So when you put them in solution, they don't really ionize in either direction very much, right? That's our small x, small change to equilibrium that we deal with, right? So you get the same relative concentration of each of them in solution, right? So you can just mix them together and they don't necessarily convert into one or the other. Especially if depending on the ionization constant, they could stay exactly the same, right? Or we can have a solution of a weak base and its conjugate acid. So if we have ammonia, what would be the conjugate acid of ammonia? Maybe that's what it was. Yep, it would be NH4. That's exactly right. So we would have NH4, and that would give us a positive charge, right? That's our ammonium ion, and generally when you add that to solution, right, you're not going to add a positively charged liquid, so you add another, right? So this is ammonium, this would be a potassium, ammonium. Oops, sorry, it should be ammonium chloride, put it this way. Added two positive charges on accident. All right, you add a counter ion, and that's generally how you're going to add it to solution, right? So this would be ammonium chloride. So it's still useful to be able to identify conjugate pairs when we're looking at buffers, because when you make a buffer solution, you're going to be working with conjugate pairs. And this was ammonia, which is our weak base. And what would be our generic base equation? So I wrote the acid equation up there. What would be our base equation when we put it in water? How does it act as a base? We have our base. It reacts with water, so this is the same as it ever was. And what do we get on the right-hand side of this reaction here? You get a hydroxide ion, right? Because that's how bases work. They change the OH concentration in solution, which we know is equivalent to changing the H3O plus concentration because they change inversely, right? And then what's the other product? What did the base do in this case? What does it do in terms of protons? It gains a proton, right? So it'll be HB plus. Right, so that's our generic base equation. I'm just leaving that there just to, that's a slight review of what we talked about before. Right, so these are the two mechanisms by which a buffer solution works, right? We have both conjugate acid and conjugate base, weak base and conjugate acid, or weak acid and conjugate base present in solution, and they work to neutralize incoming acid or base. So if we have a weak base in solution, right, and we add acid, right, we get a neutralization reaction, right? So what should always be a product in our neutralization reactions? Water, right? We should always have H2O in a neutralization reaction, right? So when we add acid to our weak base, or our conjugate base here, right, the conjugate base then consumes the extra proton from the H3O plus to generate water and the weak acid, right? So we don't get a change in H3O plus concentration by adding the acid to solution, right? Which means the pH shouldn't change very much. It does change slightly, but not very much, right? Because we still kind of shift this equilibrium of HA and A minus, so that'll affect the pH of the solution, but it's a very small change compared to having just water in solution, right? Because we're using the, in this case, conjugate base to consume the acid, right? So we get a neutralization reaction. If we have a base that's added to the same solution, right? So this is our still buffer system 1, which again was the weak acid and conjugate base. Now we're adding OH minus, or a base, to solution, right? And now we have the weak acid that's going to be used to then neutralize the OH minus that's added to solution, right? So this proton from the weak acid is going to get donated to the OH minus to then create water again, right? We want water because the water is going to not change our solution, right? It's going to leave our solution neutral in terms of pH. So we just get a small change in pH, which we know is equivalent to changing the pOH of that solution. All right, so all we're doing right now is we're just writing the neutralization reactions for our buffer system, right? And we have 2 neutralization reactions depending on the type of buffer, right? One, we should resist a change in pH if we add base to solution, and we should also resist a change in pH if we add acid to the system. Any questions on the first buffer system and how that works? Right, so we're still thinking about how acids and base works to then create water. In the second buffer system, we have our weak base. So when we add acid to solution, the weak base gets converted into its conjugate acid. Right, so then this system was the weak base plus conjugate acid. So the weak base gets converted by adding H3O plus into the conjugate acid. And again, we have a byproduct of water. And then if we were to add base to solution, we would have the inverse then again, right? We would have the weak, or the conjugate acid, react with the base added to then make water. And so again, this is kind of just depending on what frame of reference you're looking at it from, right? If we're looking in terms of a weak base or a weak acid, those are really identical to each other, which is why everything we do is kind of related to, the auto-ionization of water. And so again, if we have this one, now we have a base that's going to be added to solution. We make more of our weak base in this case, which causes just a small change in the pH. And we'll look at exactly what that change is in a little bit and ways that we can simplify those types of calculations. All right, anyone's still writing this? Okay. And so So if we have a change in pH and we're monitoring the change in pH with a buffer solution, so we're adding, let's say, OH to a buffer system, right? And this would be the volume of OH minus added. And if we're looking at the pH of the solution, initially, what should happen when we add solution? Let's say we start our initial pH initial is like 4 or something like that. All right, so we start here. What should happen as we add base to the solution? Like if we're looking, so now we're looking at this graphically, right? So how does that look? What did your guys' plots look like when you had your buffer solutions in lab a week ago? We'll have two curves, right? We'll do water, and then we'll do for the buffer, right? So when it was water, right, your initial pH started at 7, right? Because water is neutral. When you add base there, what happens? Let's say we'll just start over here of just pure water. Which direction does the pH move when you add water? It should go up, right? A more basic solution has a higher pH. So that's going to start going and changing right away to a high pH, right? If we have a buffer system, what should happen to the pH of the solution as we add base to it initially? Is your hand up, Steve? Yeah. So it shouldn't go down and then up. It'll probably stay the same at least, right? It might go up a little bit, right? When you initially add base to the system, you are going to change the H3O plus concentration a little bit because you're adding something that shifts the equilibrium a bit. But it should probably stay mostly flat. And then it'll start to go up, right? And once it starts to go up, then it'll end up reaching whatever the same pH is for the water system, right? And so at this point, right, this is usually the end point of a titration. What do you think that point represents? If we're adding, let's say our system is a weak acid buffer system. All right, what's the chemical reaction by which a weak acid buffer works to resist a change in pH by adding base to the solution? Right, if we're adding base, right, we know that we're adding that to the solution, and we have a weak acid buffer system, what's going to react with that in our neutralization reaction, right? Because we know one of our products is going to be what for sure? Water, right? In our neutralization, we're always going to have water, and we just need to figure out how is this weak acid buffer system working? Right? How are we going to create water? What are we missing? Filling in the blanks here. Anyone have an idea? Riley? Yeah, we need a hydrogen on this side, right? So for our weak acid buffer system, the two things we had were our weak acid and our conjugate base, right? So the weak acid is going to go on which side, the reactant side or the product side? The reactant side, right? Because that's the only way that we can donate this proton to the OH minus to then get our water on the other side, A minus aqueous. right, so this is how our weak acid buffer system works to resist a change in pH when we're adding OH minus to the solution, right? So at this point, this is technically the end point of your titration, right? And you guys probably titrated a weak acid in the past to determine the pKa. But here in terms of a buffer system, we're looking at it from a slightly different perspective. So what do you think happened at that point? Why is the pH changing in this case for this specific system? Right, in terms of these things down here, specifically one thing. What do you think happened as soon as the pH started changing? Yeah, all the weak acid has been used up at that point, right? So at this point, all the weak acid has been used up. Right, so now once we've used up all the weak acid, our buffer can't work anymore because now we can't resist a change in pH. We can't go to this neutralization reaction anymore, which means that we're just adding base to solution now, and it's just changing the pH of the solution. Right, so this is just the example of a weak acid buffer system, but you could analyze a plot like this for all the 4 different scenarios that you looked at in last week's lab. Right, so this is the essence of what we did in lab last time. And so today we're also going to talk about, well, what makes a buffer effective, what things affect the buffer, is there a range at which the buffer can work, and then looking at how we can simplify this calculation, looking at pH of buffer solutions. All right. So again, buffers resist a change in pH. They contain both weak acid and its conjugate base, or a weak base and its conjugate acid. So in the weak acid buffer system, that does what to added base? Right, so in the system, what happened when we added base that we just... It neutralized, right? So it neutralizes the added base when we add it to the buffer system. And in that system, if we add acid to it, what would then neutralize that acid? Yep, it would be the conjugate base that neutralizes the added acid. Right, so with weak acids and weak bases, we are looking at relationships between pH, pOH, pKa, pKb, Ka, and Kb, right? And we're looking at their relative equilibrium in water, right? That's how we determine the pH of solutions. With buffer systems, the way they work is we're looking at their neutralization reactions and how is that going to affect the pH of the solution. All right, so now I guess we have one example before, but we'll start looking at our last ice tables of the semester, at least in lecture. But if we have these different solutions, which one of these would you classify as a buffer solution? And why or why not would you classify that as a buffer solution? So I'll give you guys a second. Yeah, because this is a strong acid, right? So this is a strong acid, which means that, chlorine ions are not going to be a strong base, right? And if you have sodium chloride, table salt, you don't get a basic solution when you add table salt to water, right? You just get a neutral solution when that happens, right? So strong acids don't have a conjugate base because you don't get the reverse reaction at all, right? So this is a strong acid, so this can't be a buffer solution. What about HNO3 and sodium nitrate? So nitric acid and sodium nitrate. Is nitric acid a strong or weak acid? It's a strong acid, right? So it's the same reason as the first one. This is also a strong acid, which means that this is not a conjugate base. Sodium nitrate would just be a strong electrolyte in solution. You would not get the reverse reaction happening at all, right? So this is a strong acid, so it can't be a buffer system, right? You need a weak acid conjugate base or a weak base conjugate acid, right? And what about here? Would this give me a buffer solution? Is nitrous acid a weak or strong acid? This is a weak acid, right? So that's okay. This is a weak acid. So that's fine. But what about sodium chloride? Is that going to act as a weak base in solution? No. So for the same reason that hydrochloric acid doesn't have a conjugate base, sodium chloride is not going to be our conjugate base, right? So this is not a conjugate base. So that leaves the only one that we could have is the last one. This is going to be our buffer solution, and that's because we have its conjugate base, right? The conjugate base pair and the weak acid here, right? So we have a weak acid and its conjugate base, right? And its conjugate base acts as a weak base, right? If we have its conjugate base, the equilibrium constants are related by that relationship. So that's how we can get the equilibrium constants for a conjugate acid-base pair. Which means that despite how large or small this is relative to the water ionization constant, the conjugate base is going to have the opposite, right? So if this is a strong weak acid, that is going to be a weak base, right? And vice versa. So that would be our only buffer solution, right? We need both of them to resist a change in pH. The other solutions, for example, if you had nitrous acid just there, if you added base to solution, the weak acid would consume the base, but if you add a acid to that solution, it won't, right? So that disqualifies it from being a buffer solution, right? So this would resist a change in acid added, but not base because we don't have any conjugate base present in solution. I flipped those around. In base added, but not when we add acid, right? Because the weak acid is there to donate a proton to hydroxide, but the weak base is not there to accept a proton from H3O plus if the solution is added. All right, so we can identify buffer solutions just based off of the two different weak acids or in the conjugate base or the weak base and conjugate acid that we add. And we can also determine the pH of the solution, right? So they can be calculated similar to weak acid or weak base pH solutions, right? Which is generally the steps involve usually writing your equilibrium reaction, right? We write our equilibrium reaction. Then we set up what to calculate equilibrium concentrations? Set up an ICE table to calculate the equilibrium concentrations. And then we use the equilibrium concentrations to calculate the pH, right? So we use equilibrium concentrations to calculate pH, right? And so this again was our just extra step that's added to our generic equilibrium problems, right? It's just using the equilibrium concentration to calculate the pH. or POH. All right. So here we have a buffer solution that's prepared. It's 0.1 molar acetic acid and 0.2 molar sodium acetate. If we are at just standard conditions, what would be the pH of this buffer system, right? So this is without looking at anything specific to buffers. This is something that you can calculate beforehand, right? So we have two things that are added to solution. And so this is going to be our equilibrium reaction, right? And to calculate the pH, we need the equilibrium concentration of which one of these species in here. All right, so this is just to show that it's a strong electrolyte. Because we're asking what is the pH of this buffer system, and that's relevant, right, for your body. If you have a buffer system, like we'll have a worksheet to go over, in your blood that resists a change in pH, you want to keep the same pH in your blood because all of the biological molecules in your body, their protonation states depend on the pH of the solution, right? And if you change the charge of your proteins, your DNA, your RNA, the lipids in your membranes, you die, right? So you want to keep the pH the same in your blood. So how do we determine the pH? Right, so we have our equilibrium reaction. What do we need to know the equilibrium concentration out of everything here to get the pH of this solution? Yeah, we need the concentration, the H3O plus concentration, to calculate the pH of this system. All right, and so the first step was writing the equilibrium reaction, which I'm going to write again on the next page. So we have HC3, what was it? C2H3O2, C2H3O2 plus H2O goes to H3O plus C2H3O2 minus. Right, so what was the next step after you write your equilibrium reaction? You set up your ice table, right? So we have ice. I stands for what? Our initial concentrations, right? C is our change and E is our equilibrium, right? So this is what we want to solve for again. And then once you have your equilibrium concentrations, you use what to solve for your equilibrium concentrations, right? What relationship, once you have all of your equilibrium concentrations for each of these, what do you use to solve for concentrations at that point? Yeah. So we'll come back to that. We'll fill in the ice table first, right? So what are our initial concentrations here? What is it for acetic acid? We have 0.1 molar for acetic acid. For water, what do we do with water? We ignore it because it's a liquid state of matter. Those don't come into our equilibrium relationships. Those don't affect the position of the equilibrium. What about H3O plus? 0, right? Because we're just putting this in solution. We don't have any H3O plus initially in solution. And then what about our acetate ion? What's the concentration of that going to be? It should be 0.2 molar, right? So this buffer system is exactly like when we looked at solubility equilibria, except we have a common ion in solution, right? When we have a buffer system, we have starting equilibrium concentrations on both sides of our reaction. And so which direction does this reaction move? So I see some people saying right, and if you didn't know that it moved right, how could you determine if it moved right? Aurelia?
The H2O has emission starts at 0.
Yeah, we know that this is starting at 0, so we're probably going to move towards the side that has no product or no concentration there, right? We could show that analytically because if we calculated Q, QA in this case, it would be H3O plus C2 H3O2 minus over HC2 H3O2. And Q would be equal to what in this case? 0, because H0 plus concentration is 0, right? These are initial concentrations, so that would be equal to 0. Our equilibrium concentration, our equilibrium ratio should be what?
You know,
1.7 times 10 to the minus 5, right? So is that larger than 0? It's very small, but it's still larger than 0, right? It's a very small number, but it's still greater than 0, which means that Ka is greater than Qa, so that means that we're going to move towards the products in this reaction, right? So that's how you do it. Generally, if we start with something with 0 concentration, we're always going to be moving in that direction. So that means the sign should be what for our acetic acid in this case? What should the sign be, positive or negative? Negative, because we're losing that on the way to equilibrium. And what about for H0 plus and acetate? Positive for both of these, right? And we don't have any funny stoichiometry here, right? Because our acid-base reactions are always usually in 1-to-1 molar ratios. So then we're just going to define this as X for each of these different changes, right? So then our equilibrium concentration is 0.1 minus X, and 0.2 plus X. So that's what we set up the whole ICE table is just to find these concentrations, right? We found them in terms of some arbitrary variable. We need to solve for what that variable is first. And so how do we use the information we've been given to then solve for X here? Yeah, you use Ka, you use your equilibrium constant, right? Which is equal to H3O plus equilibrium concentration, C2 H3O2 minus concentration over HC2 H3O2 concentration. Right? And these concentrations, when we set it equal to Ka, are the exact equilibrium concentrations we have here, right? So that's why we plug those into our equilibrium expression. So we get X, 0.2 plus X over 0.1 minus X. So we could set up a second degree polynomial and use our quadratic formula to solve for this, but what else can we do with this problem? We can assume it's small because Ka is very small, right? So Ka is much smaller than 1, which implies x is much smaller than 1. All right, so we can assume all of these are small. And that simplifies our calculation a lot, right? Because now we have 1.7 times 10 to the minus 5, right? So plugging in our Ka value is equal to x times 0.2 over 0.1. We can rearrange this, multiplying 0.1, dividing by 0.2, 0.1, 0.2. Just cancel out on this side. So we get 1.7 times 10 to the minus 5, 0.1 over 0.2 equals x. I'll continue on the next. So if we plug that in, 0.1 divided by 0.2 times 1.7. You should get about 8.5 times 10 to the minus 6. Am I good to go on to the next page? Are people still writing? So that gives us x is equal to 8.5 times 10 to the minus 6 molarity, right? Because this is in units of concentration. And so how do we use that to find the pH? Yeah, it's just a negative log of that, right? Because x is just equal to our concentration of H3O plus at equilibrium, right? So when you plug that back in, it's just equal to that. So that's equal to minus the logarithm of H3O plus concentration, and our H3O plus concentration is just equal to x. So we get minus the logarithm of 8.5 times 10 to the minus 6. So times 10 x to the y, 6 negative, enter. Logarithm. We get the pH of the solution is around 6.07. All right, so calculating the pH of a buffer solution is exactly the same as calculating the equilibrium concentration of perhaps an ion in a solution that has a common ion in it, right? All it does is it just gives us another term on the other side of the equilibrium, right? Whereas usually we're starting off with 0 of our conjugate base and our H0 plus. Here we just have a little bit on the other side already. All right, any questions on that specific example? Oh, thumbs up, thumbs to the side. I know this is very similar to what we kind of went over on the exam. And so, because of the simplifications we made in solving this problem, you can actually derive a relationship that makes calculating pH of buffer solutions a lot easier. Right? And so what that method is called the Henderson-Hasselbalch equation. And this is just, so now you don't have to worry about equilibrium concentrations. You do everything in terms of the initial concentrations of the buffer components, right? And the buffer components were just the weak acid and conjugate base, or vice versa, the weak base and conjugate acid. So if we have a weak acid buffer system, give you guys a second to finish writing. If we have a weak acid buffer system, then we know the equilibrium constant is equal just to the ratio of the aqueous species, right, of the products over the reactants. And we can make an assumption that when we reach equilibrium, they don't really move very far, right? We saw the change in H3O plus concentration was pretty small there, and that means that the change in the concentrations of A and HA were very small, right? So they were about 10 to the minus 6, and the initial concentrations were 10 to the minus 1. Right, so that's about 1,000,000 times difference in those values, right? So it was like 1 part in a million in that number is what changed, right? So that's what we do when we make the small x approximation, right? We just assume that that change is very, very small. And so what we can do is we can replace the minus and plus x that we had in that reaction, right? Because initially these would both have A minus plus x, and this would be HA minus x. All we're doing in the Henderson-Hasselbalch equation is we're just assuming that these are both small. And so we can take the logarithm of both sides of our equilibrium relationship to then find a relationship between pKa, the pH of the solution, and the ratio of conjugate acid, or conjugate base, and weak acid. Right, so we take minus the logarithm of both sides. We get minus the logarithm of Ka is equal to minus the logarithm of H3O plus A minus over HA. We can just split things up because of definitions that we know. For example, we know minus log of Ka is equal to what? The pK, which tells us how strong of a weak acid we have, right? This is defined as the pKa minus the logarithm of H3O plus is equal to what? The pH of the solution. So we're going to separate that from the logarithm because we know that that's going to be equal to the pH, right? So this is equal to minus the logarithm H3O plus minus the logarithm of A minus over, or plus the logarithm over HA. And so that's going to be equal to the pH oh, that was a negative sign. Minus the logarithm of A minus over HA. So we get the pH is equal to the pKa plus the logarithm of A minus over HA concentration. Right, so we just derive this relationship because we're assuming that the changes on the way to equilibrium are small, right? So now we can use initial concentrations to look at the pH of the solution. So that means for a buffer system, whatever the pKa of your weak acid is, or the pKb of your weak base, that's going to kind of give you a range for what pH range that buffer system will be affected in. And because that gives you a range, right, that means that the only way you can really modify the effectiveness or what will affect the pH of the solution has to do with the relative amounts or differences in amounts of your conjugate base and your weak acid here. Alright, so if we start off with a different amount of conjugate base than the weak acid, this number changes, which will then affect the pH of the solution more. So the effectiveness of your buffer is going to depend on these types of things. And we can just look at this equation and then think about that. And then if we start thinking about, well, when we had a strong acid or strong base added to a weak acid or weak base, how did that affect the pH of those solutions? Well, whenever we added a strong acid or strong base to a solution, we assumed that reacted, all of that reacted first, and then we did an equilibrium concentration. So when we're adding strong acid or weak base to these solutions, all that's going to do is change the initial concentrations of these species here. All right, so that's we're going to go through how do we use the Henderson-Hasselbalch equation versus an ice table. And really they give you the same answer because you're doing the exact same thing. You would get to this relationship if you just did all the algebra we just did every single time you did an ice table. Okay, all right, so let's take like a 10-minute break. We'll come back, go through one example, and then I have a bunch of examples for you guys to kind of get some practice using buffer solutions. All right, let's go ahead and continue. All right, so we have the Henderson-Hasselbalch equation now. And so if you're trying to prepare a buffer solution, you just find a buffer solution that has a pKa, or a weak acid or weak base that has a pKa or pKb that's close to the desired pH. Right, because if you have something that's close to the desired pH, right, again, I'll write the Henderson-Hasselbalch equation right here, Pa plus logarithm of A minus over HA. How could you ensure that you have a pH directly equal to the pKa? Under what conditions do you have that scenario? When is the pH of your buffer solution equal to the pKa of your weak acid? When the log term is equal to 0, right? So this is pH equals the pKa when the logarithm A minus over HA is equal to 0, right? Does anyone know when the logarithm is equal to 0? When the inside is equal to 1, right? So what does that mean physically for the system? Yeah, we start with the exact same amount of conjugate base and weak acid, right? So this is when we have equal conjugate base and weak acid, right? Or HA equals A minus. So if you want to find a buffer solution for a specific pH range, all you have to do is find a pKa for a weak acid that matches that pH, and then start with equal amounts. we can then fine tune that pH, right? So this just means we can fine tune that by adjusting the acid base ratio, right? So that just means adjusting HA or A minus over HA. So if we want to increase the pH from the pKa, I'll give you guys a second to write, then I'll go on to the next slide. If we want to increase the pH, right, what should we do with our buffer solution? Right, how are we going to increase the pH, right? So if we start with pH, let's say 4, and want to increase it to 5, how are you going to adjust the acid-base ratio to increase the pH of your solution? Give you guys a second to think before. Right, if we want to increase the pH, then what is the sign of this need to be, right? This was our Henderson-Hasselbalch equation, pKa plus logarithm A minus over HA. What does the sign of this term need to be if we want to increase the pH range of our buffer? All right, what's the sign of this whole thing, right? So if our, let's say our pKa is 4, and we want our pH to be 5, we can adjust to 5 by changing this ratio here. So what would this whole thing have to be equal to if we want the pH to be 5 in that case? Yeah, it needs to be positive, right? Or in that case, it would be equal to, need to be, that whole thing would need to be 1, right? So this needs to be greater than 0, right? And the way it's greater than 0 in the logarithm is that implies that A minus needs to be greater than HA, right? When it equals 1, that's kind of the switching point when the logarithm goes negative and positive, right? You know, we talk about equilibrium, that special point when things balance, when we're talking about supersaturated versus unsaturated solutions. The logarithm, things are negative before the argument equals 1, and then positive after the argument equals 1. All right, so we're just looking, okay, this needs to be larger than 0 because that's what the mathematics tell us, and then physically that means that we need to have more conjugate base than weak acid when we start the solution. So we can adjust the amount that we need to get a pH range that we want. If we want to decrease the pH, that means that this ratio needs to be what? Yep, it needs to be negative, right? And that implies physically what that means is that the concentration of conjugate base needs to be less than the concentration of HA. So the buffer is naturally at around the range of the pKa of whatever the weak acid or weak base it is that you're using. You can adjust that range by adjusting the weak acid weak base or conjugate base ratio. Right, and we can see that just by analyzing how this equation has to change if we're trying to increase the pH on the left-hand side or decrease it. Okay. So if you have a pH, or you have a buffer solution containing 0.1 molar NH3 or ammonia and 0.2 molar ammonium, and you're given Kb, what would the pH of this solution be? Alright, so you're given the pKb and a you're not given the pKb, you're given the Kb of a weak base, right? Our Henderson-Hasselbalch equation is in the form of not the Kb or the pKb, but in terms of what? The Ka and pKa, right? So we need to find the Ka first, and then find pKa, right? That's the first step, because we need that to find the pH of the solution. Do we have everything else we need in the Henderson-Hasselbalch equation, right? We have pH equals pKa plus logarithm A minus over HA. Is everything else given to us? Bless you. Bless you again. Are we given the initial concentrations of HA and A minus? Yeah, we're given the initial concentrations of the conjugate pairs here, right? It's given to us in terms of a base, so it's reverse of how we would normally think that it acts. But we do have the initial concentration. Another way you could solve this is you could do the Henderson-Hasselbalch equation to show that the POH is equal to the pKb plus the logarithm of HB plus over B. All right, so you could find the weak base Henderson-Hasselbalch equation, which wouldn't be a bad exam question or something to do the exact same thing we did for our base equation that we did for our acid equation. But we're not going to do that here. We'll convert to pKa first. So how do we get the Ka from the pKb, or from the Kb?
Didn't we do Ka times Kb?
Yep, Ka times Kb is equal to what?
Kw.
Kw, right? And so then we can get Ka from there. So we get Ka is equal to 1.0 times 10 to the minus 14, our water ionization constant, over 1.8 times 10 to the minus 5. So that's 1 divided by 1.8 times 10 to the minus 9, which when we plug in, we get 1 divided by 1.8 equals 5.5 times 10 to the minus 10 is our Ka. And how do we get the pKa from that?
Negative log.
We take the negative log of the Ka equals our pKa. So that gives us minus the logarithm of 5.5 times 10 to the minus 10 times 10 x to the y, 10 minus, take the logarithm. That gives us a pKa is equal to 10.26. And then how do we find the pH? Yeah, we put it in our Henderson-Hasselbalch equation, right? So we get the pH is equal to 10.26 plus the logarithm. And in this case, which concentration do we put in the numerator and what do we put in the denominator? What goes in the numerator, 0.1 or 0.2? It should be 0.1, right? Because that's our weak base in this scenario, right? So we're using our HB plus H2O goes to H3O plus B, right? So we just reversed our base equation, right? Our conjugate acid acts as an acid in this solution. It creates H3O plus, so that gives us where we place B and HB in this case. So we get 0.1 in the numerator and 0.2 in the denominator. So you get 10.26 plus parentheses logarithm 0.1 divided by 0.2. Is this ratio going to be larger or smaller than 1? It should be smaller, right? We're dividing something by something larger than itself, right? So that ratio is smaller than 1, so that means the sign of that term should be what? The whole logarithm. Is it going to be positive or negative? It'll be negative in that case, right? Because we have more of the acid than we do the conjugate base. In this case, we have more of the conjugate acid than we do the weak base. So that means that the pH of this solution will be less than or more than 10. It should be less than, right? And you should get something about 9.96 is what the pH of this solution should be. And so for this problem, we use the Henderson-Hasselbalch equation to find the pH of this solution with the initial concentrations. How else could you find the pH of this solution without the Henderson-Hasselbalch equation? Yeah, you could set up an ice table like we did before. Your initial concentrations are going to be on either side of your reaction arrow. You set up an ice table and get the equilibrium concentration of H3O plus. Right, so both of those would be equivalent, and they'll both give you the same answer. Why? Because, both of those are going to give you the same answer, because in this ratio right here, you would normally have a plus x, minus x. You're just assuming that those are small in these cases, which is true for most weak acids and weak bases. Deja?
This method, you can use it for other reactions besides like this.
Could you use this for, you could use this for, the only thing is that you don't really have something that is defined like the pKb for other reactions, right? The pKb is kind of how we look at how strong ionization is for weak acids and weak bases, right? So if you had a term like that for strong electrolytes, you could do the same thing for like complex ion formation maybe, if the stoichiometry worked out right, because then if you have coefficients of like 4 and 5, then you have exponents and stuff in here, right? We just don't usually have something like pH or pKa for other systems that we define a lot of times. If you did the logarithm of both sides, it would still come out to give you an idea and answer the solution, but there's really no pH defined for something like an electrolyte. Right. And that also tells you that if you don't have a buffer solution, right, you can't use the Henderson-Hasselbalch equation, right? If it's just a weak acid or a weak base, right? Because that's when you assume the x is small, so that's still a valid assumption for weak acid and weak base. But what happens to this equation if you don't have a buffer solution? one term in there is gonna not look right. Yeah, you would either have 0 of your conjugate base, so in this case, yeah, or if you had 0 of your weak acid, right? If you have a 0 in there at all, logarithm of 0 is undefined, and then logarithm the other way would be logarithm of something undefined, or logarithm of infinity, right? So as soon as you start to get to the edges where you have very little of one of the species, either the weak acid or its conjugate base, all of a sudden the Henderson-Hasselbalch equation isn't defined for that anymore, right? So this is pretty, if you have any large changes to equilibrium, all of a sudden this doesn't work anymore. So this is mostly used for buffer solutions. All right, any questions on this, right? So how do you guys think this is easier or harder than ice tables? Or more straightforward? Or it's a little bit more straightforward, right? Because you're not going through all of the, the different charts and everything. We're doing the same thing, right? Mathematically, we're doing the same thing. We just took a couple steps of the algebra. This equation kind of combines solving for x and then plugging it into minus logarithm of the H3O plus concentration. That's all that equation does. Okay. All right, so let's take just a little bit of time to then discuss how we deal with adding acid or base to a buffer solution. So when we add an acid or base, this will cause a slight change in pH, right? So if we think about our plots of the pH versus the volume of the acid or base added, it slightly starts to increase or decrease at first. It's pretty flat until we use up all of our buffer, right? Once we use up all of our buffer, the pH starts to change a lot. And so the same way with weak acids and weak bases, when we had a strong acid, weak base, or weak acid combination or mixture, we separate it into two calculations. You do the same thing for these systems as well, right? So you start off with a stoichiometry calculation. Because you're adding a strong acid or strong base to the solution, you assume that that dissociates right away, and then you do your equilibrium calculation, which in this case is our Henderson-Hasselbalch equation, right? So this is our equilibrium calculation, and this is used to find our initial concentrations. The only difference with a buffer system, though, is when we add the weak acid or weak base, what happens to that weak acid or weak base? And not weak acid, strong acid or strong base. When we add that to the system, what happens to it in a buffer system? If we add sodium hydroxide or hydrochloric acid. It dissociates, yeah. And when it dissociates, you get hydronium or hydroxide in solution, right? So this, when you add NaOH or HCl, you get OH minus or H3O plus in solution. But what happens in a buffer to those things when you add those to solution? All right, after it dissociates, what happens to H0 plus or OH minus if you have a buffer there? So you think about the plots, right? You're adding OH minus or H3O plus. What happens as you're adding it to a buffer? What happens to the pH of the solution if you're adding OH minus or H0 plus to a buffer? What did your buffer plots look like for last week's lab? Increased for the buffer system. How much did they increase? A lot or a little bit?
A little
just a little bit, right? All right, so the pH is just changing a little bit when you add it to a buffer, whereas water, it did what? It shot up or shot down right away, right? So what's happening to the H0 plus or OH minus when you have a buffer there? Or if the pH isn't changing at all, what's happening to the H0 plus concentration if we're adding acid, if the pH isn't changing? It isn't necessarily decreasing, right? Because it's still going up just a little bit, right? The pH, so it is a slight decrease, right?
Is it being suppressed?
Yeah, we're not changing the H0 plus concentration very much, right? We're just changing it very little, right? Which means that something has to be happening to H0 plus because we're adding H0 plus directly to the solution, right?
So
Lee?
H3O plus gives away hydrogen and then form water.
Yeah, we create water and a salt basically, right? And so what do we call that when we create water when we add strong acid or strong base to a weak acid or weak base buffer system? What kind of reaction is it? Neutralization, right? So the H0 plus or OH minus is being neutralized in this case, right? So when we're doing this first step, we have to think about our neutralization reaction, right? We need to think about how our buffer system works, how it reacts with what we're adding, and then we always need to have water as a byproduct, right? So this gets neutralized in a buffer. So we need to think about our neutralization whenever we're dealing with this, right? Are we adding base or acid? So if we're adding the base or the acid, what's it reacting with? The weak acid or its conjugate base? The weak base or its conjugate acid? Right? And then you just do a stoichiometry calculation. You assume all of the strong acid or strong base reacts with whatever that buffer component is to create water. And then that gives you your new initial concentrations. Okay, so what does that look like? So here we have a acetic acid buffer system and acetate buffer system. And we want to see what happens to the pH of the solution as we add sodium hydroxide to the solution. Right, so here we're given in terms of moles, which is fine. We can do everything in terms of moles. If we had a volume, then we would then just look at the, and we actually do have a volume. It's a 1 liter buffer solution. Right, we're adding salt, so that's not going to change the volume at all. So these are in moles or molarity is fine. If you have a mixture of different volumes, you have to take that into account. But in this case, everything works out. And we have equal amounts of acetic acid and sodium acetate. So if we add 0.01 moles of hydroxide, what's the first thing we need to do? We need to do our stoichiometry. Right? We need to do our stoichiometry calculation to see what happens to that base as it's added. Right? So this is a strong base. So we have a strong base, and we know that it's what's going to happen to a strong base in a buffer solution. What type of reaction is going to happen? A neutralization reaction, right? So that's going to be neutralized, right? So this is going to be neutralized when we add it to our buffer system. So we need to think about what is this neutralization reaction that we're going to go through. Right, so what is the neutralization reaction for this? We know we have OH minus on the reactant side because we're adding that to the solution, right? So we know we have that because that's what we're adding to the solution. We're adding a salt of sodium hydroxide. And then we have what on the product side are we guaranteed to have? Water, right? We're always creating water in our neutralization reaction. Which means we're going to have acetate and acetic acid to fill in the blank. So which one is going to go where? How do we neutralize hydroxide? Which one is that going to react with? Acetic acid or acetate? acetic acid, right? Because we need to gain what to become water? We need to gain a proton to become water, right? So the only way we gain a proton is something that donates it. The weak acid is what donates the proton. So we get HC2, H3, O2, and then here we have the conjugate base. C2, H3, O2 minus. Both of those are aqueous. All right, so once we have our neutralization reaction, then we can see how all of the moles are shifted as soon as we add the strong base to this solution. So we start, I'm going to write our neutralization reaction again down here, OH minus plus HC2, H3, O2, H2O, plus C2, H3, O2 minus. And at the moment, before mixing, we have 0.1 moles of acetic acid. We have 0.1 moles of acetate and 0.01 moles of sodium, of hydroxide, right? We mix them together. We know that all of that hydroxide that we add is being neutralized, right? So then we mix. So all of this gets neutralized. The acetic acid is what consumes it. Did you?
Sorry. You know that all of it is being neutralized
Because
because it's a strong base?
the hydroxide, as soon as it gets into a reaction, is an extremely exothermic and favorable reaction. So that's the physical reasoning for why you know it happens.
If it was like a weak base?
If it's a weak base mixture, it doesn't work the same way anymore, and then you have to do ice tables again. Remember, we had the 2 weak bases, and even then you really didn't worry about it because you just looked at which equilibrium constant was larger, and that dominated the pH, because that suppresses the ionization of the other weak acid as well. But yeah, so for strong acids, strong bases, you're always assuming all of it is going to react right away. You assume all of it reacts right away, and then we deal with whatever's left over. Yeah, good question. Okay, and the reason that this happens, it's guaranteed to happen, is a very exothermic, favorable reaction. If you've ever done a neutralization reaction, usually the solution gets hot right away. And so then we add 0.1 mole, right? So we calculate these numbers to get our new initial concentrations, right? So this is going to be 0. This is going to be, what is it, 0.99. And this will be 0.11, 0.099, 0.099. Right, so this is the first step in calculating the pH of the solution. The second step is then just using our Henderson-Hasselbalch equation to then calculate the pH of the solution. Right, we're given the pKa, the Ka, which allows us to find the pKa of the solution. We know the new initial concentrations of our conjugate base and weak acid. And so we can use all that to solve for the pH. We could also do an ice table from this point, where these are initial concentrations, and then you set up an ice table as well, using those as your initial concentrations. Is everyone comfortable with this step so far? So the important thing for this step is to write the neutralization reaction. Understand that that happens with all of the conjugate base, all of the strong base or strong acid that you added. Then you calculate how that affects the new amounts of everything in solution, and then you calculate the pH. So then you can see right away that if you add too much, you go past your buffer limit, all of a sudden this doesn't work anymore because then you're gonna have negative amounts of certain things on the solution. Okay, so the next step is then calculate the pH, which is the first thing we have to do is calculate the pKa. And the pKa is equal to what? Minus the logarithm of what? Ka, which is minus the logarithm of 1.8 times 10 to the minus 5. Minus 5. I feel like we already did this exact buffer system, so I should know what it is. 1.8 times 10. 5 minus the logarithm, that is 4.74. Then we find the pH using the concentrations that we just had. Right, so the pH is equal to 4.47 plus logarithm of 0.099. Oops, sorry, other way around, 0.11 and 0.099. Right. Based off of what we added to the solution, what would you expect to happen to the pH relative to the pKa? Right? The pKa gives us the starting point for the buffer region, right? So if we add base to that, do you expect the pH to go up or down? Up, right? Because basic solutions are higher pH. Which means that if we look at our Henderson-Hasselbalch equation, this ratio should be larger than 1 because we should add a positive number to that, right? Based off of how our neutralization reaction worked, we start off with equal amounts. Now we've added more conjugate base because of the neutralization reaction. So this ratio is now larger than 1. So that it makes sense physically that the pH is going up in our solution. So we have 0.11 divided by 0.099 logarithm plus 4.47. So we get a pH of 4.52, right? And if we compare these values, we see that the pH did go up. It only went up a little bit, right? So the buffer is working. Normally, if you add 0.01 moles of sodium hydroxide, that's going to change the pH by quite a lot. But we have a buffer there, which means the pH has only changed slightly since that point.